Okay, Assalamualaikum dan salam sejahtera. So kita akan sambung semula pengajian kita berkenaan dengan velocity triangle. Okay, So in this section, I would like to discuss with you about velocity triangle, and please make sure that you could understand the velocity triangle very well, because velocity triangle is the most important element in centrifugal pump, because all the calculation, all the way we solve centrifugal pumps problem is actually based on the velocity triangle. And velocity triangle is actually changed relatively to the angle of blade. Okay, that's why you cannot just remember the shape. Okay, the best one is you could draw your own velocity triangle based on your understanding. Okay, I will teach you how to draw, how to write the velocity triangle in this in this section. So I hope you could give attention for this lecture. So this is the velocity triangle. So what you see here is velocity triangle because we have a triangle here. So we have in inlet here, for example, we have a triangle like this one. We also have triangle of this one, and we'll also triangle of this one. So at the outlet here, so we have a triangle here. So we have another triangle here, and we have another triangle here. So that's why we call this as a velocity triangle. So, and then, okay, velocity triangle here is in linear velocity. So mean the unit here is meter per second. And the blade here is actually rotate at certain speed, and it will rotate in RPM. That's why I said in previous lectures, you need to understand how to convert the RPM here to the linear velocity, because in velocity triangle the unit is meter per second. However, the rotation of blade here, the rotation of impeller is in RPM or radian per second. So mean the blade rotates in rotational speed. Okay, here this is the omega. Okay, so we go step by step to explain the velocity triangle. Okay, first you need to draw the blade. So the one piece of here is called the blade. Okay, so this is the blade. So there is a lot of blade. Okay, so this is also the blade. Okay, this is also blade. Okay, there is so, and then set of blade is called the impeller. Okay, to draw velocity triangle, so we focus on one blade like this one. Okay, it is okay for you to take the middle, the center line between these two blades to draw your velocity triangle. Okay, okay, the basic idea is, okay, just forget about the velocity triangle. First, you need to know the basic idea how water flow inside the blade. Okay, as I said, water comes from the center point here. We call it as I, mean the center point. The water comes from here. Okay, and then the water will flow in radial. Okay, so in previous chapter, we learned about the phenomenon when water comes from one single source. So we call it as source. So the idea of source is water water come from one single point here, and the direction of flow is in radial direction. So mean the water flow is in radial direction. Okay, this is the ideal condition of the system. So, and then because we have two blades here, okay, we have two blades here, so for sure water will go into this line. Okay, just imagine water go through the center line of the blade like this. And then, okay, at the same time, blade here is rotate at a certain speed. Okay, let's see here, we have an omega. So means that the blade here is rotate at certain speed. So the direction, the rotation direction is this one. Okay. So again, so water from here, it's flow in radial direction. So and then the water will flow the center line here. So and then it will go out like this one. Okay. So this is the basic idea. So when water traveling from this point to this point, okay, there is an energy transfer. So the energy, the kinetic energy from the blades here will be transferred into the fluid flow here. So means that that's why it is important to make sure that water flow from inlet point to outlet point here. Because at this area, so the energy being transferred from blade to water. Okay, and then after that, at this point, okay, at outlet point here, water will have a lot of energy. Okay, so because it has a lot of energy, now it can move faster or it can flow to the higher level. Okay, that is the mechanism how energy being transferred into the inside the blade. So and then, so we would like to see the how we could draw the velocity triangle. Okay, the first thing that you need to draw is we need to draw the real velocity. The real velocity. Okay. So in this situation, we call it as the absolute velocity. Okay. So the real velocity or the absolute velocity. So what is that one? So it is actually means the real thing, the real phenomenon that occur in the pump. So the absolute velocity is actually referred as V1 here. The V1. So you just imagine that the water comes into this direction and then it will go into the blade and then it will come out as like this one. So we write for inlet, we write as V1, and for outlet, we write as V2. Okay, so to simplify this one, okay, let's say first you need to draw your blade. So this is the first step to draw your velocity triangle. And then the second step is please draw the real velocity, the real flow that occur inside the pump. So we call that as absolute velocity. So the absolute velocity means that you just imagine if the blade is rotated from right to the left with a counterclockwise like this one. So the real flow, the real fluid will enter like this one and comes out like this one. Okay, we call it as V1 and we call this as V2. So this is the first step that you need to draw. So the real flow or the real velocity. Okay, I'm sorry. So the real flow here or the absolute velocity, okay, the or absolute velocity is actually the real one. So means that if you have one piece of paper here, so this paper will travel to this one, to this point, and then it will travel on this line. So, and then this piece of paper will stay here, and then this piece of paper will flow to this direction. So means that the real flow or the real velocity or the absolute velocity is actually the real velocity that occur inside that pump. So this is the real one. You could measure the direction, you could measure the velocity, the magnitude. Okay, that's why this is very important for you to draw the absolute velocity, the real one. Okay, so you just imagine that if we have blade like this one, and this blade is rotate counterclockwise or from right to the left, okay, and then we will have a V1 like this one and V2 like this one. Okay. Okay, I make it simple. So we have a blade here. So, and then we have a rotational speed of blade like this one, counterclockwise. And then we draw the absolute velocity, V1 here and V2 here. Okay, because this is a sketch, so it is okay for you not to draw exactly with the angle and so on and so forth. It is okay. But the direction is correct. The direction must be like this. Okay, so this is about the velocity triangle. Okay, then we go for the next step. Okay, if you see here, so if you see here, we have V2 here, or we have V1 here. At the same time, we have U1 and we have VR1. And at this here, we have VR2 and we have U2. Okay, so now I would like to explain about the VR2 and U2. Okay, so the VR2 and U2, okay, the VR1 or VR2, and also the U1 and U2, this four velocity is actually the component velocity. The component velocity. So means that the U1 and VR1, U2 and VR2 is actually an imaginary velocity. Okay, you need to understand like this. For example, we have a river here, a river flowing from right to the left, and then you have a ship here. So, and then this ship is moving in reality from here to here. So in mathematics, we could say that, so this is the resultant velocity, and then we could have a component velocity of this direction and this direction. Okay, same goes to this situation. So we have absolute velocity here, mean the resultant velocity here and here. Now we could divide it into its component, which is component that relative to the blade. So VR here, so the word R here means relative. So means that if the blade is something like this, so means that the velocity will enter the blade at the same direction. And then if the blade is like this, the angle is like this, so means that the water will flow out at this angle. Okay. So means that the VR here means the velocity which is relative to the shape of blade. Okay, so means that you need to do like this. So, and then the word, the term of U1 and U2 is the velocity regarding to the rotation of impeller, rotation of blade. So means that because the blade is moving counterclockwise like this one, so means that the U, the velocity component regarding to the motion of blade will be like this one. So, and then it is also must be like this one. Okay. So means now we have, this is the VR1, this is the U1, and this is the VR2, and this is the U2. Okay. Okay. Another thing that you should know here is the V1 here is the resultant velocity, means the real one, the real velocity. V1 is real velocity, V2 here is real velocity. So this velocity, U1, U2, VR1, and VR2 is the component velocity. Component means the imaginary velocity. So, and you know, the V1 here is the resultant velocity. So means that the vector here must close to each other. So it must start from here, go to this direction, and then from this point, it close loop the resultant velocity. Okay, this is the idea of when you draw a velocity vector. So this is the resultant vector. You must make sure that all the vector here will close loop. So it will go from here to here, and then it will go back from here to the end of the resultant velocity. Okay, so this is the first velocity that we want here. So we have the real velocity, V1. So, okay, and then it has component velocity, which is the U1 and the VR1. So the U1 here, okay, is the velocity regarding to the rotation of impeller. So normally it will become the tangent of this one. Okay. The VR1 is the velocity relative to the shape of blade. So if the blade shape like this one, so it will enter at this angle. Okay, so the VR2 here, so it's relative to the angle. So you could imagine that the shape is something like this. So the direction is like this one. And then the U2 here is the component velocity regarding the motion of impeller. So means that it is the tangent for this point. Okay. So now you could draw your first velocity component. So one is VR2, VR, and one is U. Okay. However, this velocity is actually cannot help us in solving problem in centrifugal pump, because this triangle doesn't have any 90 degrees, any perpendicular angle. So means that we cannot use trigonometry to solve this problem. So we cannot use sine, we cannot use cos, and we cannot use tangent because it doesn't have a 90-degree angle. Means that we need to create another triangle to make sure that we could use the idea of trigonometry to solve this problem. Okay, so we go for the second triangle, which consists of VF1 here, and we have a VW here, V world here. So how to draw this one? Okay, let's say again, we start with our blade. So, and then our blade rotates counterclockwise like this one, means from right to the left. And then, remember, we have the real velocity. Okay, so the real velocity is V1 here, and we have velocity of V2 here. Okay, so this is the real one. So then, okay, as I said, this is the real one. Okay, so if the real velocity flow without any friction, mean in ideal condition. Okay, I hope you understand the meaning of ideal condition. Means when the flow didn't have any resistance. So it's similar with the theoretical. So as I said previously, if the fluid flow without any resistance, so mean in ideal condition, the flow will same like a source. So you learn about source and sink in previous chapter. So the source here means the water will comes out from one point, and then it will flow directly in radial direction. Okay. However, why in the first place we draw our V1 here a little bit shifted like this? Because there is a resistance. Because for sure in real application we cannot neglect the friction. We cannot have a real application without any friction. That's totally impossible. So what, because we understand that the friction is exists, that's why we shift a little bit the absolute value to become like this one. So, and then what happened to our velocity triangle? So we have blade here. So it's rotate from counterclockwise, from right to the left. So this is our real velocity, V1. And then if the if the fluid flow without any resistance, it will flow in radial direction. So we call it as VF1. So the word VF here is referred to the flow. Mean it's referred to the ideal flow. Mean flow without any resistance. Okay, why? So because why the real velocity flow at this shifted direction? Because it has resistance. So this resistance is called VW. Okay, so we call VW, and VW here is referred to whirl. So it is pusaran. So means that because we have a turbulent one or we have resistance, so the flow a little bit shifted. Means the real flow is a little bit shifted from the ideal condition. So that's why we need to draw an arrow from here to here, and then it continue from here to this one, because the V1 here is the real velocity. It is the resultant velocity. So I hope you could understand. So we have a resultant velocity here. So mean another vector must be from here to here to here to here, and then it must close loop the situation. So this is the way we draw the vector. So in this situation, we only have two components, which is the turbulence. We don't call the velocity turbulent here. We call it as the V whirl. Okay, it is pusaran. Okay, and then the other one is VF1, means that velocity of the ideal flow. Okay, or we we simplify it as the velocity of flow, means that the velocity that show us the ideal condition of the flow. Okay, in this situation, we already have a perpendicular angle here. So we have a 90 degrees angle here, means that now we could use our trigonometry. So at the outlet here, so we have a V2 here. So and then we have a VF like this one, VF2, and we have the V whirl 2 here. Okay, and then we merge all these velocity components, and it will become like this one. So it is actually the combination of two ideas of a velocity triangle. So we merge it at one, and then we have this one. Okay, let's say we look it closer here. Okay, I enlarge this one. So this is a very important one. So I hope you can understand this. Okay, this is the real velocity. Okay, why it is shifted a little bit? Because we have turbulence, we have resistance. So what we don't call it as a turbulent, we call it as whirl. So WHIRL. So this is the velocity of whirl. Okay, this is the velocity of whirl. So and then this is the ideal velocity. So means this is the theoretical velocity. Okay, so this is the first velocity triangle. And the second one is, so this real velocity, okay, is actually, it's also can be divided into two components. Okay, component that are relative to the blade shape. So we call it as the velocity relative to the blade. So which is the VR1 here. And also, this is the blade relative, the velocity relative to the shape of blade. And from here to here is the velocity related to the rotation of the impeller. So it must be tangent of this one. Okay. So this is the, so we use superscript 1 here to show the inlet, and we use the subscript of 2 for the outlet. Okay, so this is the velocity for outlet. Okay, so this is the resultant velocity, the real velocity that occur inside this pump. Okay, so this is V2. So all the components here must be reflect the resultant velocity. So we have velocity that reflect the angle of the blade, so which is R2 here. So and then velocity which is reflect the rotation of the impeller. So this is the U2. Okay. So and then we have another component velocity, which is the ideal one. So this is the ideal velocity. So we call it as VF2. And then why the V2 here shifted a little bit, because there is a turbulence, there is losses. Okay, we call it as whirl. So WHIRL. So it is actually from here to here. Okay. So this is two types of velocity. So we combine it in one page, in one schematic sketch, call it as a velocity triangle. So I hope you could draw this. Okay, I show you again. So because this is a very important part, so I hope you could draw it carefully. Okay, so let's say first step, you need to draw the blade. So this is your blade. Then you need to mention the direction of your rotational speed. Okay, so let's say it is rotate from right to left. It's create a counterclockwise rotational direction. Okay, that is the first step. So the second step is you need to draw the actual velocity. You need to draw the actual velocity. So which is, the idea is simple. If your rotational speed here is from right to the left, so for sure the absolute velocity will become this one. So mean it also move from right to the left. Okay, this is, so we draw the actual velocity as V1 and V2. So point 1 here, okay, is the inlet, and point 2 here is the outlet. Okay, the third step. Okay, the third step is you draw velocity according to the design of the blade, design of the pump. So there are two designs. One is about the blade and one is about the impeller. So and then we draw the velocity relative to the shape of blade. Okay, because the shape here is like this one. So now we draw the VR1 like this. And because the shape is something like this, so for sure the velocity is flow like this one. So we draw as VR2 like this one. Okay. And then because the rotational speed is counterclockwise, rotate from right to the left like this one. So the tangent velocity is also from right to the left. So we draw like this. So it is okay for you just to draw a horizontal line like this one to show that it is tangent of this point. So this is just to simplify your drawing. Okay, so it is a tangent line of this one. Okay, we mention it as U2 here, and we have the U1 here. Okay, so this is the third step. So, and then the fourth step is to draw the component velocity to show the theoretical velocity and also to show the resistance. So the theoretical velocity must be in radial direction. So it is okay for you to draw like this one. So let's say we have the VF1 here and also the VF1 here, VF2 here. So just draw it vertical. It's okay. Okay. So and then why the actual velocity, which is the V2 here, is not the same with the velocity for theoretical. So it's not same because we have resistance, we have friction, we have turbulence occur on that one. That's why the theoretical velocity or the theoretical direction is not the same with the real direction. So because of that one, we need to draw another component that show the turbulent one. So the turbulent is become from this point to this point. So we write as V world 2, and here from here to here is V world 1. Okay, so now you have a complete set of your velocity triangle. So, and then another thing that you should know here is please make sure that your velocity triangle is actually in a right direction of vector. Okay, for example, we have a V1 here, and then finally you draw the VF1 here. Okay, please bear in mind that the V1 here is the resultant velocity. So this is the resultant vector. So the V1 here, okay, it must be from here to here. It must be in closed loop. So this is the resultant. So it must be start from here, and then it continue from here to here, and then it go to the end of the vector. Because sometimes student will draw, okay, we have a V1 here, so we have the okay, let's say we have the VR1 here, so this is the U1. So and then student draw this is the V1, and then he don't know where to write, so he just write here as V1. So if you write V1 at this area, so means that you have the resultant velocity here, V1. So you have component of VF1 here, and suddenly you will have it here. So it's something not right. Okay, maybe you could say that, oh, this is a vector, we could reverse it for this one. Okay, that's it's 50-50, not 100% correct, because the distance here from here to here may be different from the distance from here to here. That's why you need to put it at the correct location, because it will give a lot of difference in the calculation later on. Okay, in example of calculation, you will find that if you make mistake, put wrong direction or wrong place for your vector, so it will affect your calculation. So means that maybe you cannot get more than half from full marks of these topics.